Hi, my name is Miranda.
My name is Ronghe.
My name is Leon.
My name is Jonathan.
My name is Selena.
And we are Miracle STEM Engineers.
This is our design review video. We will first go over the mission, the software, the hardware, and lastly, we will put together all the sections in our integration and test plan slide.
Think smart. These are our SMART requirements. For S, the CubeSat shall be able to detect wildfires through the images and collect data using images taken. For M, the CubeSat shall operate for at least a year. For A, the CubeSat shall monitor a minimum area of 25,000 kilometers squared daily. And for R, the CubeSat shall prioritize regions with higher wildfire risk. And finally T, the CubeSat shall take an image every minute. How will we verify the requirements? For our specific requirement, we will conduct simulations and real-world testings to test its detection accuracy. For our measurable requirement, we will monitor the CubeSat's operational life by tracking performances, for example, its uptime over a year. For the attainable requirement, we will measure the area covered daily by the CubeSat using its image data. And with our relatable requirement, we will check if the CubeSat's algorithm targets wildfire-prone areas by comparing its focus with zones known with higher risk. Lastly, for our time-bound requirement, we will check the imaging frequency of the CubeSat by reviewing timestamp image logs. It should take at least 1 image per minute as specified.
Here is our concept of operations. So there's 3 phases to the concept of operations, which include the pre-launch phase, the launch phase, and the orbit phase. The CubeSat will begin in the off state, and when it is powered on, it will begin by running a diagnostics check. So this means it will attempt to execute the code on the ground. If that fails, the CubeSat mission cannot be continued and it will lead to a mission failed. But if it passes, we're able to proceed to the launch phase. The launch phase begins by attempting to calibrate the sensor with the script sensor calc v2. Afterwards, gyroscope configuration and accelerometer configuration will be attempted. The gyroscope configuration will come first, and if that fails, the mission will have to terminate. But if it passes, we are able to attempt to configure the accelerometer. The accelerometer configuration, if it fails, the CubeSat is able to be resent to Earth using the gyroscope because the gyroscope configuration has passed in this step right here. And if the accelerometer configuration passes, we're able to continue to the orbit phase. So in the orbit phase, the CubeSat will initiate a camera setup. If this fails, again, the CubeSat will be resent to Earth using the gyroscope. But if the camera setup passes, we're able to run the main part of the CubeSat, which is the fire detection script. If the fire detection script passes, this will lead to a mission success because our mission has been completed. But if the fire detection script fails, the CubeSat will still remain in orbit because all the other parts of the CubeSat work just fine, and ground station will attempt to update the CubeSat remotely, and if it is unable to do so, there's a 24-hour limit, and then the CubeSat will be resent to Earth using the gyroscope to start again from the very beginning of the pre-launch phase, this off state right here. And now moving on to the system level block diagram. In the power block, the solar panel captures sun energy and charges the battery, which directly powers the Raspberry Pi 4, the central processing unit of our CubeSat. There is a micro SD card attached to the Pi as storage for the software we run, and also the mission data that we gather. So the Pi is also connected to a Pi 3 camera module, which is the payload of our CubeSat, and this captures data in the form of images. The Pi is also connected to ADCS sensors, and this includes the accelerometer, which tracks linear movement, the gyroscope, which tracks angular movement, and finally the magnetometer, which helps orient the CubeSat. And the Raspberry Pi and the CubeSat is able to communicate with the ground station thanks to the uplink, which sends commands from Earth to the satellite, and downlink, which sends collected data back to Earth for analysis. And this is done all through the communications units of the Raspberry Pi 4, which include the transceiver and the antenna.
For software, our mission will be to detect wildfires using our CubeSat camera and then collect data for the wildfire for every time interval. And that will be the area of the wildfire so we can analyze how much the fire has spread. So using the data, we will then plot a graph with the y-coordinate being the area of the fire and x-coordinate being the time measured in minutes. As for a more specific plan on how to accomplish our goal, we will first take pictures every minute using auto camera v2.py, and then we will use imaging techniques to isolate the wildfire sections in the image and then calculate the areas for that. And then at the end, we will use matplotlib to graph the values that we collected. So far, we have written a draft of the code illustrating our ideas for how our code should work. So right here, we have 3 different lists. Data 1 and Data 2 will be storing the data values for the area of the fire that we calculated, and time x will be storing the time that we calculated the area. So right here, we have a loop that runs depending on max cycle, which in this case will represent the amount of time that we want the data to be collected, which is 30 minutes. And for each cycle, we will run the calculate area function to get the areas, and then we will append it back to Data 1 and Data 2. So right here, we adjust the settings of the graph to make it more clear to us so we can actually look at the comparisons between the areas of the fire in different times. So right here, we have the calculate area function. So first, we create 2 different masks to be used to isolate the wildfires in the images. So we have a mask for darker red and mask for lighter red. And after we calculate the areas, we return it back to the main function to be used. So right here. So our next steps will be to test our code and fix any errors that come up, and then we will add more complexity if possible to make our data results more accurate.
Here is the mechanical layout of our CubeSat. We used many different pieces to create it, including acrylic plates, aluminum brackets, and corner pieces. Here is the CAD model of our CubeSat. We created this CAD model by CADing the individual pieces on separate files and then piecing them all together in one single assembly.
This is our link budget. Our team thought of 3 different situations where the connections between the CubeSat and the ground station will differ. So we have situation 1 where the CubeSat is directly overhead the ground station, which means that we'll have a pretty strong signal and we have a good connection because it is close to the ground station. And then we have situation 2 where the CubeSat is farthest away from the ground station. We have changes in the connection, and that means that we have a weaker signal. While situation 1 and situation 2 are under favorable weather conditions, we consider that there might be unfavorable weather, such as storms that will distort the connection between the CubeSat and the ground station. While it is stronger than situation 2, it is still weaker than situation 1.
Here's our power budget. Firstly, what we have on top is the table of values for when the solar panel was rotating parallel to the sun, along with its graph. What we did was that we stopped at every 30 degrees we rotated parallel to the sun and recorded what data we had on the adapter, which is why we have from -90 to +90 degrees in the first row and the voltage, current, energy, and power beneath it. And a little different to the one above, here on the bottom we have the table of values for when the solar panel was rotating perpendicular to the sun in this line graph. For -90 and -60 degrees, it wasn't facing the sun at all, so no sun energy was absorbed, which is why there's no data shown on the adapter for these 2 angles.
Here is the mass budget of our CubeSat. We weighed out the individual pieces and calculated the total mass. The total weight came out to 1.138 kilograms with a cost of $284.90.
This is the data budget for our CubeSat. Similarly to our link budget, we thought of 3 different scenarios where the data budget for the CubeSat would differ. The first situation, when the CubeSat is directly overhead, is where the data transfer between the satellite and the ground station is most efficient. The second situation, where the CubeSat is farthest away from the ground station, results in a much less efficient data transfer. Finally, in the third situation of unfavorable weather conditions such as heavy storms, the data transfer would be the least efficient.
And here's our last section, integration and test plan. Here's a diagram illustrating all of our sections being put together. So at the top, we have data budget, power budget, and link budget, which will help us know about the capability of the CubeSat so we can learn how to plan out our smart requirements and goals. For concept of operations, it will help to plan out our software architecture, and with the functions already given to us, which is sensor calc and auto camera, it can help us write our fire detection code. And for mass budget and materials, as well as system level block diagram, we can use it to help plan out our hardware and CAD, and this will lead us to our end results. Thank you so much for listening.